Today I'll be deriving Kepler's first law in Cartesian coordinates, but I'm going to use polar coordinates only once, and I'm going to use it right now. So without further ado, let's start the proof. So we know that dA dt is constant because I proved Kepler's second law in one of my previous videos. And we also know that area in polar coordinates equals this, where r is a function of theta. So r is a function of theta equals area. And hence, if an integral is just a reverse derivative, if we take a derivative with both sides, or let me just illustrate. So let's say we have some r theta. If we take a derivative of this with respect to time, it would become r prime theta times d theta over dt. And hence, if we take a derivative on this side and this side, we get 1/2 r squared times d theta over dt, because the integral cancels out with the derivative equal, and we need to apply chain rule. So d theta dt is the chain rule equal dA over dt. Hence, the change in area also equals this. But what does d theta dt mean here? D theta dt is actually the angular speed, but it's not in the sense you know it. So let's say in the elliptical motion, the part of the planet is here, and it's moving this way. And let's first consider what 1/2 r squared times d theta equals. Let's just remove the time, and let's just consider the area. What does this area equal? Well, if this is r, this is simply a portion of the circle. So if we were to draw a circle, oh yeah, this is not a perfect circle. So it would be this area right here. This area right here would equal 1/2 r squared d theta, as proved in my previous video where I found the area of a pizza slice. So that's what 1/2 r squared d theta means. Now, is it always the case that d theta times dt, or d theta over dt times r equals velocity? No. It always equals velocity perpendicular though. So if we were to draw this, and this is not a perfect ellipse, it's going that way. Velocity perpendicular is the velocity that's perpendicular to the radius, because as we see here, it's also going this way too, because angular speed only considers circles, not ellipses. So yeah. So we know v perpendicular equals d theta dt over r. So let me write down this again. 1/2 r squared times d theta over dt equal dA dt. We know dA dt is constant. Let me draw a better ellipse. So we do this. And let's say there's some v initial, and there's some r initial, where r initial is the initial distance between the sun and the planet. Now, if we know d theta dt times r equal v perpendicular, and this v naught is already v perpendicular, we can say that 1/2 r squared times d theta over dt equals 1/2 v naught times r naught, because we know d theta dt times r is v perpendicular, and v naught also equals v perpendicular, because initially it's already moving perpendicular to the sun. So we get this identity, that because this identity, yeah, where dt equals v naught r naught. Let that sink in. Remember, r times d theta dt equals v perpendicular equals v naught, because v naught here is already perpendicular, so it's already v perpendicular. So if we multiply by r, well, we get d theta over dt times r squared equals v naught times r naught. And hence we know that V naught R naught is conserved. Or, never mind, not V naught R naught, but we just know this is conserved, alright? And this equals V naught R naught. Alright. So let's go to the next step of the proof. And let's draw the ellipse again. Now, I want to consider the acceleration of the planet in the x direction. So let's make this the actual acceleration, this the acceleration in the y direction, and this the acceleration in the x direction. Let's make this theta. Hence, this side right here would be negative a cos theta, and this, since it's going downward, this would be negative a sine theta. And if you use Pythagorean theorems, you'll find out this works out. So hence, d squared, the acceleration in the x direction equals this, negative a cos theta. And a, as we, if Newton is correct, is gm over r squared. That's acceleration. So we can plug in a here to get d squared x over dt squared equals negative gm cos theta over r squared. Alright, let that sink in. Now, here's what I want to do. We discovered this identity, right? And r squared also equals this, v naught r naught over d theta over dt. I want to plug in r squared here. So hence, we get this, d squared x over, or I don't need to write it here. I just get negative gm cos theta over v naught r naught over d theta dt. And we can just bring d theta dt into the numerator. So let's go to a new page. So remember this. So d squared, or never mind, acceleration in the x direction just equals gm v naught r naught times cos theta times d theta dt. Because we just brought the d theta dt to the numerator. And let's take an integral of this. So if we integrate, we get that acceleration becomes the velocity. And this just equals the integral of gm v naught r naught cos theta d theta dt times dt. And this would just equal gm, oh, whoops, I forgot the negative sign. So we can just put the negative outside the integral. I put the negative sign there. So this would be negative gm v naught r naught. Oh, this would be sine theta. Wait, does the theta cancel? Oh yeah, the negative sign is still there. And yeah, so we get that dx dt equals negative gm v naught r naught sine theta. And yeah, now I need to, what I'm doing is seemingly random, but I need to prove many things first before I actually can prove that that all planets move in an elliptical motion. All right. Now, I want to find another definition of d theta dt. So what's another definition of d theta dt? Well, I know that in an ellipse, if the focus is at the origin, and there's some theta here, and this is y, and this is x, I know that y over x equals tan theta. Let that sink in. Alright. Now, if I take a derivative on both sides with respect to time, I'd get this. Well, if we use, what do you call it? Division rule or whatever. Division rule for derivatives, we get this. So we get dy dt times x minus dx dt times y over x squared equals sec squared theta times d theta and dt. And I want to bring your attention to this identity. And hence, if we divide everything by cos squared theta, we get tan squared theta plus 1 equals sec squared theta. And we already know what tan theta is. Tan theta equals y over x. So if we bring it down here, sec squared theta would equal 1 plus y squared over x squared. And hence we can plug sec squared back into here. So let's first divide both sides by sec squared. And hence, if we expand sec squared theta, we get this. X squared times 1 plus y squared over x squared. Let me rip out this page. And x squared, let's distribute x squared. We get that d theta over dt equals dy dt times x minus dx dt times y over x squared plus y squared. Remember, we're trying to find d theta dt. I divided both sides by sec squared theta, so I can isolate d theta over dt. So this is what d theta dt equals. And x squared, r squared equals x squared plus y squared. If we look at the diagram of the ellipse, this component here would be r, and we can see by Pythagorean theorem that y squared plus x squared equals r squared. And hence, the denominator is just r squared. Let that sink in. And hold on. Let me think of the next step. Yeah, it's gonna. Oh yeah, d theta over dt times r squared equals dy dt times x minus dx dt times y. And as we've proved before, hold on, where's the sheet? Right here. R squared times d theta dt also equals v naught r naught. So this also equals v naught r naught. Let that sink in. Alright, now remember this. And now let's go to a new topic. So let's go back to the original. We're trying to original formula of an ellipse, or the particular ellipse where our foci is at the origin. So that would look something like this. C squared or a squared equal 1. Now, let's isolate x so we can find its derivative. So we get this. X plus c squared over a squared equal 1 minus y squared b squared. X plus c over a equals 1 minus y squared over b squared. X equal a. Minus c. And let's take a derivative of this. By the way, dx dt also equals dx over dy times dy dt. Yeah, I just know this. So if we take a derivative of this, well, this is just constant, becomes 0. So dx dt also equals a 2 if we apply chain rule. And, well, the 2's cancel out. If we simplify, we get this. Alright, and that's what we get. Let that sink in. And let me, hold on, where do I go from here again? Yeah, I need to prove a lot of random things that even I can't keep up. let me think here. What did I need to prove? Oh, right. So I'm gonna check this out. So as I said before, dx dt equals dx over dy times dy dt, right? And I also proved before that v naught r naught equals d theta over dt times r squared equals, let me use this as reference, equals dy over dt times x minus dx over dt times y. And hence, we can remove this dy dt if we rearrange. So dy dt would equal v naught r naught plus dx over dt times y divided by x. So I basically set this part equal to that part, and I isolated dy over dt. And let me check my work. V naught r naught, that to the other side, and divide by x. All right, this works out. And hence dx dt also equals this. Dx dy times v naught r naught plus dx dt times, that's a y, over x. And I want to isolate dx dt. So hold up, how do I isolate it? Let's distribute first. And this would become, let's bring this to the other side. Let's isolate dx dt. And I'll need more space for this. So if you look here, oh yeah, and let's divide everything. So we get this, that dx dt equals dx dy times v naught r naught over x over 1 minus dx dy times y over x. Alright, now this looks like a messed up function. So let's multiply both sides by x. So times x. This is basically like multiplying by 1, so we get the same answer. So if we multiply both sides by x, we get this. Dx dy equal, whoops, sorry. Over y. Alright, and this equals dx over dt. Now, we're almost there, Now I need to remember what I need to do. Alright, let's multiply both sides by dy over dx now. And hence this is what we get. Alright, and now we need to find what dy dx is. And that would be pretty simple. So if we go back to our formula, x plus c squared over a squared plus y squared over b squared equal 1. And hence dy, if we need to separate y first. So I'm just going to do it really quickly in my head. That's what y equals. and hence dy over dx would equal, I'm going to do it really quickly in my head again. Oh, there's no dx dt, because I'm only taking it with respect to dx. And let me check my work. So to the bottom times 2, chain rule, negative 2x plus c, oh, times a squared here. Yeah, I usually mess up here. Let me see. Is that the derivative? I think I've made no mistakes. Alright. So this formula right here, now we plug in dy dx. We plug in dy dx. Hence we get this. We're almost there, almost there. Dx over dt equals v naught r naught. Well, this is dy over dx, right? So let me think. Alright. Negative x, let me work really slow here so I don't mess anything up. Minus y. Alright, so that's what dx dt equals. And we can further simplify this because, well, hold up. What is 1 minus x plus c? Okay, so we get this. 1 equal x squared. Hence, this equals y squared plus b squared. And, yeah, so dx over dt also equals v naught r naught over negative xb x plus c over a squared root y squared over b squared minus y. And we can further simplify this to dx dt equal negative v naught r naught. I'm taking this negative out, so both terms on the denominator would be positive, and I'm moving b up there. So we get this, x b squared x plus c over a squared over y plus y. Work this out. So we have this. Now, we can do this. Dx dt equals negative v naught r naught x b squared x plus c over a squared times y plus, let's multiply y by a squared y on the top and a squared y on the bottom. So we get a squared y squared over a squared y. And hence we can combine these and we can move a squared y to the numerator. Hence dx over dt equals negative v naught r naught times a squared y over x b squared x plus c plus a squared y squared. We're almost there, we're almost there. Now, there's something I proved a long time ago, and we need to bring that up. Oh yeah, right here. Dx dt equals negative gm v naught r naught sine theta. So right now we know dx dt equals both of these. So let's set them equal to each other. All right, so we know these equal to each other. So what are the conditions where I have made a successful proof that the motion of something moving in a Newton type force is an ellipse? Well, the sole condition is if I can get one side to be a constant equal a constant. If I can achieve this, I've proved that anything moving in a type of force like this is moving in an ellipse. So what I mean is like, let's say I achieve something like v naught times r naught times, or this is just random by the way, gm over v naught r naught squared equals a. If I do this, I get constant equal constant, and that means I proved that, I already proved Kepler's first law. So if I can manipulate this equation so that all the y's and x's cancel out, so I'm only left with a constant times a constant, then I'll be good. All right, and sine theta can also be written as y over root x squared plus y squared, I believe. All right. So all I need to do is to manipulate these functions so I get a constant equal constant, and then my proof would be complete. All right. So if sine theta equal y over root x squared plus y squared, then I can plug that in for sine theta. Oh, root x squared plus y squared is just y over r, and sine theta is y over r. And I hope I don't need to prove that. This should be self-evident, I guess. All right. So negative gm v naught r naught times y over root x squared plus y squared equals negative v naught r naught a squared y over xb squared x plus c plus a squared y squared. Well, we can remove the negatives and we can divide both the numerator by y. So let's just divide the whole thing by negative y. Here's what we get. Gm over v naught r naught times 1 over x squared plus y squared root equals v naught r naught a squared xb squared x plus c plus a squared y squared. And let's move the variables. Let's move the variables to one side and constants to this side. So we got this. Let me think. Right. We can do this. Gm over v naught times r naught. Let me think. Yeah, I'm gonna need a lot of thinking. What do I want to do? So, yeah, I think I want to do that. All right. Equal, or let's make this times a equals v naught squared r naught squared. I bring this v naught r naught, dividing both sides by v naught r naught, and bring this v naught r naught to here. So hence this is y squared, and bring one of the a's there. Equal a times root x squared plus y squared over xb squared x plus c plus a squared y squared. And I also want to do something else. Let me first I want to factor out b here. So damn shit, it's hard to sit like this. All right, how do I factor out b? All right, so I can do this. b squared x over times x plus c plus a squared over b squared times y squared. And hence I can move b squared to the top. So gm b squared v naught squared r naught squared a equals a root x squared plus y squared. And I'm just going to distribute it now. X squared plus xc plus a squared over b squared times y squared. All right. Now let's go to another page. So we have, okay, and let's go back. So gm b squared over v naught squared r naught squared times a equals a x squared plus y squared. And before I write the denominator, I want to go back here. Oh, whoops. This also equals this. So x plus c squared times b squared plus a squared y squared also equals a squared b squared. Hopefully I don't need to explain how I got from here to here. If I distribute everything, I get this. B squared times x squared plus 2b squared xc plus b squared c squared plus a squared y squared equal a squared b squared. All right, and let me write the denominator back again. All right, and further, I want to split a squared. If you know your properties of ellipses, a squared also equals b squared plus c squared. So I want to convert this a squared into b squared plus c squared. So we get this. This is a b squared, by the way. And we can further simplify this to, I'm not going to write this term anymore. I'm just going to go, just consider this term because it's too much of a hassle. So if, and then this simplifies down to plus c squared y squared over, does the b squared still remain there? Yeah, I think it does. Let me consider this for a moment. I probably didn't want it to be this way. All right, let's not do that. Let's not do this. Instead, let's go a different route. Let me see here. Oh, I know. Yeah, I shouldn't have done that. All right, let me bring this b squared back here. Yeah, this is so annoying. So gm v naught squared r naught squared over a equals a x squared plus y squared. And I'm bringing the b squared back to here. All right. And now let's consider this long string. So if we consider this long string, well, b squared, x squared, which is here, plus a squared y squared, which is there, plus b squared xc is this, would equal a squared b squared minus b squared c squared minus b squared xc, because there's double b squared xc. All right. And a squared b squared minus b squared c squared also equals something else, I think. Let me see what it equals. Let me consider this. A squared equals, I think, b squared plus c squared. All right. Which equals b squared plus c squared times b squared minus b squared c squared minus b squared xc. Hence this just equals, well, these cancel out, so we're just left with b4 minus b squared xc, and hence this equals that, because this equals this equals that equals, well, this. So we get that gm b naught squared r naught squared over a equals a plus y squared over b4 minus b squared xc. Alright, and let's multiply b squared. Now we can multiply b squared back here. So gm b naught squared r naught squared times a times b squared equals a x squared plus y squared b squared minus xc. And let's square both sides. Well, if we look here, a squared x squared plus a squared y squared. If we square both sides, we get b4 minus 2b squared xc and plus x squared c squared. But I want to bring your attention back to our lovely formula here, which we converted to this. And hence, what does b4 minus 2bx squared x squared c squared equal? Let me think here. Let's just consider for a moment this. Well, we know c squared equals, or remember this formula. So let me think, thinking. All right, let's look back here. So we have this formula, right? All right, let's first convert this c squared here into a squared minus b squared. So we get something like, should I do that? I don't know. All right, let me think. I'm really close to the end result. I just need to think here. Let me rewrite this here. Bx squared plus 2b squared xc plus b squared c squared plus a squared y squared equals a squared b squared. As from here. All right, now I don't need to look at this. Shoot, what is... All right, let's convert this b squared into some... Let's convert b squared into, well, a squared minus c squared. So we get a squared x squared minus x squared c squared plus 2b squared xc plus b squared c squared plus a squared y squared equal a squared b squared. Let's isolate a squared x squared plus a squared y squared. Get this. A squared b squared minus b squared c squared minus 2b squared xc plus x squared c squared. Yeah, we're so close to this. Now, Oh yes, finally. Let's convert a to b squared plus c squared. So it would be a squared x squared plus a squared y squared equals, well, you want to convert this to a squared plus c squared, right? So c squared b squared minus b squared c squared is 0, so those just cancel out. You know, whoops, a squared equals b squared plus c squared. So we would get, oh yes, okay. I'm just gonna write it down. Too lazy to explain, so tired. All right, minus b squared, c squared, and yada yada yada. Well, this just cancels down to b4 plus c squared b squared minus b squared c squared, and hence a squared x squared plus a squared y squared equals, well, if these cancel out, then it's just b4 minus 2b squared xc plus x squared c squared. And look, a squared x squared plus a squared y squared equals this, which also equals this. So hence, gm b squared squared over v naught squared r naught squared a equals, well, a squared x squared plus a squared y squared over a squared x squared plus a squared y squared equals 1. And we've already proved that the motion of anything in space, according to Newton's law, is an ellipse. And we can just take a square root on both sides, and we get this. And a would equal gm b squared v naught squared r naught squared. And here we have a constant equal constant, hence I have proven. The reason why if I get the result to be a constant and a constant, then I've already proved my answer is let me just show you. So let's say the formula of a circle is x squared plus y squared equals r squared, right? It's hard to explain. And let's say, yeah, it's really hard to explain, but like, it's because the form, if the form of the equations look the same, where you can rearrange it and you can get like, yeah, if the form of the equations look the same, then you could get an answer where a constant equals a constant. Yeah, this is really hard to explain. It makes so much sense in my head, but can I explain it? I'm trying to think of a specific example. Oh, by the way, I can prove Kepler's third law with this, which I'm going to do in my next video, but I'm trying to explain why if a constant equals constant, then my proof for Kepler's first law is valid. All right, let me just use the formula of ellipse. So, y equal b times root 1 minus x plus c squared over a squared, right? So if I prove that something has the same motion as this, so let's say I want to say g, the y coordinate of g is an ellipse. That means gy must be of the form of this. But if this is so, yeah, so gy is an ellipse, or is part of an ellipse. So make sure part of an ellipse. So gy is a part of an ellipse. That means I can that gy equals y, and if gy equal y, then, well, I can just divide both sides by gy, or I can divide both sides by y and get 1, and I get 1 equal 1. Now it's hard to explain, but basically if the forms are the same, like if gy is the y component of an ellipse, it must have the same form as this. But this form can be reducible to a constant equals a constant. And yeah, that's why the proof works. Thank you.